All right, now I'm going to go over the next set of problems. So I'm going to be starting with number 6. Number 6 says, a small object carrying a charge of -8 times 10 to the -9 coulombs experiences a downward force of 20.0 times 10 to the -9 newtons when placed at a certain point in an electric field. What is the electric field at the point in magnitude and direction? So we have a particle, and then we have an electric field, and we place a negatively charged particle in this electric field. And we know the force. What is the magnitude and direction of this field? Key thing here, key difference is that now, instead of talking about the source charge, we're talking about a charge that's experiencing this electric force. So now, we're going to use the other equation. So for point charges, when we put a charge into an electric field, we place a charge into an electric field. The electric field is going to be equal to the force divided by that point charge. Remember, this is a negative particle. So the magnitude of the electric field is going to be that force, which is 20 times 10 to the -9 newtons, divided by Q, which is going to be that -8.00 times 10 to the -9. So putting this into my calculator, and for this problem, actually I don't even want you to worry about this negative sign yet, because we're going to be determining direction in the next part. So just look at the magnitude of Q. So 20 times 10 to the -9. Let me show you this. 20 times 10 to the -9 divided by 8.00 times 10 to the -9 gives us 2.5 newtons per coulomb. So this is the magnitude. Now the second part asks us about the direction. So reading the problem, it says a small object experiences a downward force. So the force is downward. So if the force is downward and it's a negative charge, what do we know about negative point charges? The field and the force are in opposite directions. So if the force is down, then this field must be upward. So for this problem, when we have a field, put a negative particle in this field, it's going to have this magnitude for the field, and the field's going to be pointing upward. Now, flipping over to part B, it says, what would be the magnitude and the direction of the force acting on a proton placed at the same point in this electric field? So now we don't know the force when a proton is placed in this field. So we know the magnitude of the field because it's the same field. It's 2.5 newtons per coulomb. So now what we have, we're placing a proton. So if you remember, E is equal to the force divided by little q. So force is equal to E times Q. E is 2.5. What's the charge of a proton? 1.60 times 10 to the negative 19. So 1.60 times 10 to the negative 19 times 2.5. So you should get 4 times 10 to the negative 19. So that's the magnitude. Now, we need the direction. So this is a proton. Which direction was this field? So the field from this part we said was upward. And if we place a proton in the field, the direction of the force is in the same direction as the field. So since the field was upward, the force is also going to be upward. Because if a proton is placed, the force and the field are in the same direction. Field was up, so force has to be up. Now number 7. What must be the charge, sign, and magnitude on a particle with a mass of 8.40 grams for it to remain stationary in the laboratory when placed in a downward directed electric field of magnitude 5,000? So now we are placing a charge within the field again. We know that our field automatically is 5,000. Newtons per coulomb. We know that the mass is 8.40. Times 10 to the negative 3rd kilograms. All I did was change 8.40 grams to kilograms. So I just moved the decimal place over to the left 3 times. And we are looking for Q. So if E is equal to F divided by little q, Q is equal to F divided by E. We know E, but you might be wondering, what is F? So the force that's acting on this charge can be assumed to be the force of gravity. And we remember that Fg is equal to mg. So 8.40 times 10 to the negative 3rd times 9.8. So you should get 0.08232. So the charge is going to be 0.08232 divided by E, which was 5,000. I'm sorry, this one looks a little bit more messy. So, doing that, I get my final answer to be 1.65 times 10 to the negative 5th coulombs. That's my final answer, 1.65 times 10 to the negative 5th. Now, let's read this question carefully because this is the magnitude. It says what's the magnitude and the sign. So we have a downward electric field hold on 1 second. So since we have a downward electric field and the force of gravity is upward, since they're in opposite directions, this must be negative. So it's going to be negative 1.65 times 10 to the negative fifth. So the direction is negative. I mean, not the direction. The sign of this charge is negative. So we're talking about an electron. Okay. We're almost done. Now, number 8. What is the magnitude of an electric field in which the Coulomb force on an electron is equal to the magnitude with an electron is equal in magnitude to the weight of an electron? Okay. So, right off the bat, it says the Coulombic force is equal to the weight. So, Fg equals mg. So, the mass of an electron is 9.11 times 10 to the negative 31st times 9.8. Putting this into my calculator, we get 8.93 times 10 to the negative 30th. And it says, what is the magnitude of the electric field? Electric field is equal to the force divided by the charge. So 8.93 times 10 to the negative 30th divided by the charge of an electron times 10 to the negative 19, sorry. Divided by and we get 5.58 times 10 to the negative 11th newtons per coulomb. And it just asks us for the magnitude, not the direction. All right. Last question, number 9. A uniform electric field exists in the region between two oppositely charged plane parallel plates. An electron is released from rest at the surface of the negatively charged plate and strikes the surface of the opposite plate, 3.20 centimeter distance from the first, in a time interval of 1.50 times 10 to the negative 8th seconds. Find the magnitude of the electric field. Now, this one is a very, very tricky question. So let me draw this scenario. We have a plate, and we have another plate. Oh, my plate is crooked. No, don't worry about that. And then there's an electric field in between these two plates. And then, so I am going to call this the negative plate. I'm going to call this the positive plate. An electron is released from the negative plate. It's falling down there. That's where it's falling to. So, this is little q. It's a point charge because it's within the electrical field caused by these two plates. And we're looking for the magnitude of that field. So we know that E is equal to F divided by Q. Now what makes this problem really complicated is that we don't know F. So, but what we do know is that the plates are 3.20 centimeters apart, and the time that it takes to fall from here to here is 1.50 times 10 to the negative 8 seconds. So it falls pretty fast because that's how long it takes to go there. So if we know the distance and if we know the time, we can find the acceleration. And if we know the acceleration, we can find the force. So, since we know the displacement and the time, we can find the acceleration. And since we know the acceleration, we can find the force, because force is equal to ma. So I'm going to rewrite this equation as electric field is equal to ma divided by q. So now we actually have to find a. Now, if you guys remember from Physics 1 when we did kinematics, you remember that there was an equation that said the displacement is equal to the initial velocity times t plus 1/2 the acceleration times t squared. When it first falls from this plate, the initial velocity is 0. So that means that this equation just simplifies to one-half at squared. So, solving for a, we get 2 times the displacement divided by t squared, which gives me 2 times, if the displacement was 3.20 centimeters, it's really going to be 0.032 meters divided by the time it took. This is 1.50 times 10 to the negative 8 seconds. So putting this into my calculator, good old calculator, 2 times 0.032 divided by 1.50 times 10 to the negative 8. Note that I put this in parentheses. Oops, and I can't forget to square it. So, what you should have gotten was 2.84, sorry, times 10 to the 14th. So that's just A. Now that I know A, I can plug this A all the way back up here to solve for the field. So, field's going to be equal to the mass of an electron, because an electron is falling, 9.11 times 10 to the negative 31st times that acceleration, 2.84 times 10 to the 14th, divided by the charge of the charge. And I'm not worried about sign right now, times 10 to the negative 19th. Putting all of this in my calculator. Remember, put parentheses, and then do your numerator first, and then divide it by your denominator. What you're going to get is 1618.75 newtons per coulomb. I will put in my calculator for you guys, but my phone's about to die. It's on like 3%. Okay, now, B. That was the magnitude. It says find the speed of the electron when it strikes the second plate. So the speed when it strikes the second plate. Now, we know from kinematics, what we knew here was acceleration. We got from the first part, and that was 2.84 times 10 to the 14th. And we know the distance, or the displacement, which was 3.20 centimeters, which is equal to 0.032 meters. From kinematics, we know that final velocity is equal to initial velocity plus AT. Initial velocity, like we said, up here was 0. So final velocity is equal to AT. So the final velocity when it strikes the second plate is going to be 2.84 times 10 to the 14th times the time it took, which was 1.50 times 10 to the negative 8th seconds. So I don't have time to put in my calculator because my phone's about to die. What you should get is 4.26 times 10 to the 6 meters per second. That's final velocity. All right. I hope these videos were helpful.